This is one of two tutorials on spreadsheets that we distribute in Chemistry 324. This one specifically deals with graphing. Because we don't know which one students will read first, the first couple of slides in each tutorial is the same. Spreadsheets are designed to perform calculations on data sets, and they're most useful in performing repetitive calculations on large data sets, stuff that you wouldn't really want to do by hand. The most commonly encountered spreadsheet is Microsoft Excel, although Google Documents has an more or less equivalent spreadsheet. There are slight differences, and that's something you should look into if you decide you're going to use Google Docs. Spreadsheets come preloaded with the most commonly used mathematical formulas. Laboratory experiments make extensive use of spreadsheets like Excel for calculations on data sets, again, especially large data sets, repetitive calculations, or a large number of sequential calculations. In 324, we find that the majority of our students have little experience with Excel and hesitate to use it. One of the gifts of this course, whether you're ready to receive it or not, is you're going to be forced to become more comfortable with using Excel. This tutorial is designed to get you started with graphing in Microsoft Excel. The first thing we need to cover is the proper way to enter data in Excel. And we need to note right off the top that there is a 7% error rate in manual data transmission. If you're looking at a number on an instrument and writing it down in your lab notebook, there's a 7% error rate. If you're looking at a number in your lab notebook and typing it into a spreadsheet, there's a 7% error rate. That's 7% for me, that's 7% for you. It doesn't matter who is actually recording the data. Everybody makes those errors. Decimal places move, numbers are dropped or transposed as you're writing things down. It is important to make sure that after you've typed data into a spreadsheet that you check and double check that data against your laboratory notebook. So always check your data for errors after you've entered it. At least half the time when students contact me about mistakes either in homework or laboratory experiments, it's because there's errors in the way the data has been transcribed. Many pieces of laboratory equipment can automatically produce a numeric file that can be then imported into a spreadsheet, which eliminates these errors. We purposefully, in this course, do not take advantage of those capabilities because we want you to be able to manually take data and enter it properly into a spreadsheet and learn to check for your errors. One of the common errors is actually a formatting error. Improperly defining an input as text rather than as a number. So if we take a look at the two columns of data in the table below, we will see that the first column is labeled as numeric and the second column is labeled as text. If Excel interprets the contents of a cell as numeric, it right justifies it as we have in column 1. If it interprets the cell contents as text, it left justifies it as we see it in column 2. You cannot conduct math operations on a cell that has text in it. So in column 2, you can see that the student has very carefully entered data including units. As soon as it sees alpha characters, Excel decides that you're just randomly typing text, and it left justifies it, and you cannot do a mathematical operation on that cell. Also, when we're using data in Excel, we will always enter scientific notation in the form of 1.02 e minus 3. Excel will accept either a lowercase e or a capital E. Excel has difficulty interpreting the type of format most calculators use for scientific notation. It is important to keep track of units in your data. Most people successfully do that by placing unit information at the head of the column or row of data. You cannot enter it in the cell with the actual numeric data. When you're setting up data in Excel for graphing, it's important to understand that Excel always assumes that the first row of data or the first column of data is the X data, the independent variable. So if we have our data arranged in rows, it will assume that the first row is X data, and every row after that is a different set of Y data to be graphed against the one set of X data. If the data is arranged in columns, it will always assume that the first column is your X data and every other column after that is the Y data. Excel will allow you to plot multiple independent data sets on a single graph where we have independent X and Y values. Excel will allow you to do that as two different data sets and display them on the same graph. So let's go ahead and mechanically go through plotting experimental data in Excel. The first thing that we need to review are the concepts of independent and dependent variables. The independent variable is the one that you control with your own hands is on the x-axis. The dependent variable depends on the independent variable and is plotted on the y-axis. For 324 calibration curves, the concentration of the standards that you make up to form the calibration curve is what you control and goes on the x-axis. And the instrument signal, which depends on those concentrations, is on the y-axis. Let's go through the individual steps that we need to accomplish to put these graphs together. The first thing is we're going to highlight the x and y values we wish to plot. They should be either in neighboring columns or neighboring rows, and we will highlight both columns or both rows. We will then go into the toolbar above the spreadsheet and click on the Insert tab. We're going to insert a graph, and when we plot experimental data, we always choose the XY scatter plot, otherwise we're not going to get any useful information. We always choose just to display the data points with no connecting lines. A connect the dot line has no scientific value. Eventually we'll fit this data with a linear least squares data fit, which will have some important quantitative values. Place your mouse somewhere in the white area of the graph and left click. In your toolbar at the top of the page under Chart Tools, click on the Layout tab. Click on Chart Title and choose Above Chart in the pop-up box. Give your graph a descriptive title such as Copper Calibration Curve. Now click on Axes titles. Choose Horizontal Axis and Title Below Axes. Give the axis a descriptive title, including units. We're going to repeat that with the vertical axis. Pick Rotate Title. And we're going to give that axis a descriptive title, including units. Is there a mathematical relationship between the x and y variables? Well, if the dependent variable is truly dependent on the independent variable, then the answer is yes. Excel can calculate the equation which best agrees with the relationship between our x and y variable data. Although Excel will happily fit nonlinear data, in 324 all of our experimental data is linear if the experiment has been run correctly. We're going to choose a linear least squares fit, abbreviated LLS, which gives us the best fit line for linear data. To plot this best fit line on your graph, you're going to place your mouse on one of the data points on the graph and right click. In the pop-up box, we're going to choose Add Trend Line. We're going to make sure that linear fit is checked, but that's the Excel default. And then down at the bottom of the pop-up box, we're going to click on the boxes for Display Equation and Display R-squared value. Excel doesn't know anything about significant figures, and the number of significant figures displayed for the linear least squares fit is an arbitrary default value from when the program was set up. At a minimum, always get 4 significant figures for the equations listed. 5 would be better. You can change the number of significant figures displayed by clicking on the box which contains the linear least squares equation, and then clicking on Format Selection in your toolbar, probably in the upper left-hand corner of the toolbar. In the pop-up box, select Number, and then pick the desired number of decimal places to display for this equation. When we're done making the graph of our experimental data, it's important to give some consideration to the relationships in the graph. Hopefully you have something that looks like this. This is a typical calibration curve for experiment 3, which is determining copper by atomic absorption spectroscopy. You can see we have a descriptive title at the top of the graph. We have labels on both the X and Y axis, including units. On the Y-axis, absorbance is unitless, so we have no units there. And you can see we clearly have displayed the mathematical formula y equals mx plus b for the best fit line. We also have an excellent r-squared value. Certainly for any of the data generated in 324, you should expect a minimum of 0.99 for your r-squared value. The closer to 1, the better the linear relationship between the independent and dependent variables. But we need to understand that r-squared is a measure of the differences between the data points and the calculated best fit line. It's a measure of precision, not a measure of accuracy. When plotting experimental data, we always want to look at the qualitative aspects of the data points and the best fit line. So I'd like you to look at this graph for a minute and consider, are the data points randomly scattered around the best fit line, or are the errors between the data points and the best fit line systematic? Do they form a pattern? Well, in fact, the data points in this particular graph show a systematic deviation from the linear least squares line. The high and low data points are below the line. All of the middle points are above the line. In fact, the data we have plotted here is slightly nonlinear. It would be better fit by a curve than a line. The difference is small enough it probably won't affect the calculation for your unknown in this experiment, but sometimes it's important to be noted and recorded in your lab notebook.